Hello all, welcome to this lecture of this course heat transfer. So in the last lecture we were discussing regarding the LMTD formula for the parallel flow and counter flow heat exchanger. So there we have seen the derivation of the LMTD value or LMTD equation for the counter flow heat exchanger. After that we have seen the overall heat transfer coefficient equation. Then based on all this concept and the equations we have discussed different numericals to calculate the area of the heat exchanger or the length of the tube of the heat exchanger. So all these things we have discussed in the last lecture. So today we'll be discussing another new topic, that is effectiveness NTU method. Epsilon NTU. So this NTU is the number of transfer unit, and the derivation of the formula for this NTU analysis in case of the parallel and counter flow heat exchanger we will discuss today, and based on all those formula we will discuss different numericals. Okay, so let us start this discussion. So the heat exchanger effectiveness or epsilon, it is actually defined as the ratio of actual heat transfer to the maximum possible heat transfer. So this effectiveness, the formula, it can be written as actual heat transfer by maximum possible heat transfer, which is equals to Q divided by Q max. Now this actual heat transfer, it can be represented by writing the energy balance over either side of the heat exchanger. So Q equals to m dot h Cph multiplied by the temperature difference of the hot fluid inlet and outlet. This is equals to m dot C and specific heat for cold fluid, and multiplied by the temperature difference for the inlet and outlet in case of the cold fluid. As the outlet temperature of the cold fluid is higher, so that's why it is Tc2 minus Tc1. Now there are some other terminologies, that is capital CH, this is the heat capacity or hot fluid capacity or water equivalent for the hot fluid. Then Cc, this is the cold fluid capacity rate. Then C mean, this is the minimum fluid capacity rate, it is Ch or Cc. And then the C max, this is the maximum fluid capacity rate, that is Ch or Cc. So based on the values you will say that it is C mean or C max. So the maximum rate of heat transfer for parallel flow or counter flow heat exchangers would occur if the outlet temperature of the fluid with smaller value of Ch or Cc. That means the C minimum, that is the minimum fluid capacity rate, were to be equal to the inlet temperature of the other fluid. Now the maximum possible temperature change can be achieved by only one of the fluids depending upon their heat capacity rates. That means the maximum change cannot be obtained by both the fluids except in the very special case of equal heat capacity rates. So in that case, Q max is equals to Ch Th minus Tc1 or Cc Th1 minus Tc1. So Q max, it is the minimum of these two values. It is Q max equals to C min multiplied by Th1 minus Tc1. So if it is so, in that case we can write the effectiveness, that is actual heat transfer by maximum possible heat transfer. This is equals to Ch Th1 minus Th2 divided by C min Th1 minus Tc1. So this is equals to Cc, that is the heat capacity rate for the cold fluid, multiplied by Tc2 minus Tc1 divided by C min divided by Th1 minus Tc1. And once the effectiveness it is known to us, then the heat transfer rate can be calculated by using the equation Q equals to epsilon C min multiplied by Th1 minus Tc1. So these formulas we need to remember to solve the numericals. Now what is this NTU? The full form is number of transfer unit. Now this effectiveness, actually it can be expressed as a function of three non-dimensional parameters. This method is known as actually NTU method. So this method or approach, it facilitates the comparison between the various types of heat exchangers which may be used for a particular application. This NTU, it represents the size of the heat exchanger. Now, the effectiveness for the parallel flow heat exchanger. It is the derivation for the effectiveness of the parallel flow heat exchanger analysis. Now, the heat exchange dq through an area dA of the heat exchanger. So, in case of the parallel flow heat exchanger, the temperature distribution, it is known to us. So, if we refer that diagram for the temperature distribution of a parallel flow heat exchanger, in that case dq is equal to U dA Th minus Tc. So similar equations, it is already known to us. We have seen for the LMTD derivation of the parallel flow or counter flow heat exchanger also. So this is equals to minus m dot Cph dTh. This is equals to m dot C Cpc dTc. So this is equals to minus Ch dTh. This is equals to Cc dTc. So this is the equation number 2. And from this equation number 2, you can write the formula for the dTh and dTc in terms of the heat capacity for the hot fluid and cold fluid. Now, after 2 or 3 steps, we can rearrange this equation. That means dTh minus Tc divided by Th minus Tc, this is equals to minus U dA 1 by Ch plus 1 by Cc. After the integration, we will be getting the equation in the rearranged form, that is Th2 minus Tc2 divided by Th1 minus Tc1. This is equal to e to the power minus UA divided by CH plus 1 by CH divided by CC. So this is the equation number 10.40. Now the formula of the effectiveness, it was the actual heat transfer by maximum possible heat transfer. So this is equals to CH H1 minus Tc2 divided by C mean Th1 minus Tc1. Now from this equation we can get the hot fluid outlet temperature and cold fluid outlet temperature, and the representations are 10.41 and 10.42 equations. Now if we do some mathematical calculation and some rearrangement, then after some steps we will be getting the equation number 10.43, that is for the effectiveness formula of the parallel flow heat exchanger. So it is coming, effectiveness, it is coming as 1 minus e to the power minus UA by CH plus 1 plus CH by CC divided by C mean multiplied by 1 by CH plus 1 by CC. So this is the formula of the effectiveness. Now if the CC, that is the heat capacity for the cold fluid, if it is greater than the heat capacity for the hot fluid, in that case C mean, this is equals to CH, and C max, this is equals to CC. So these are the things that we need to remember. These are actually conceptual things. So when Cc greater than Ch, so in that case we can write the effectiveness equation, that is 1 minus e to the power minus UA divided by C mean plus 1 plus C mean by C max divided by 1 plus C mean by C max. Now in this similar manner also we can write the effectiveness equation when Cc less than Ch. So in that case C mean it will be Cc and C max it will be Ch. So in this we are getting the equation number 10.44 and 10.45. So if we rearrange these two equations, then we are getting a common equation, that is effectiveness, it is equals to 1 minus e to the power minus UA by C mean plus 1 plus C mean by C max divided by 1 plus C mean by C max. Now this C mean and C max, this represents a smaller and larger of the two heat capacities, that is Cc and Ch. Now the grouping of the terms, that is UA by C mean, it is a dimensionless expression called the number of transfer units, that is NTU. The formula of the NTU, this is UA divided by C mean. Now this NTU, it is a measure of the effectiveness of the heat exchanger. Okay, this is the physical significance. It is NTU, it is a measure of the effectiveness of the heat exchanger. UA by C mean, the formula for the NTU, number of transfer unit. Now this C mean by C max, it is another second dimensionless parameter, and it is called the capacity ratio, capital R. So this capital R, that is the capacity ratio for this heat exchanger, it is C mean by C max. So the effectiveness of a parallel flow heat exchanger, it is given, can be represented in terms of NTU. So that means in case of a parallel flow heat exchanger, the effectiveness, it can be written in terms of NTU and the capacity ratio as effectiveness equals to 1 minus e to the power minus NTU multiplied by 1 plus R divided by 1 plus R, where NTU equals to UA by C mean and R equals to C mean by C max. So this formula we need to remember to solve the numericals based on the NTU concept or effectiveness NTU concept in case of a parallel flow heat exchanger. Now in this similar manner we can derive the effectiveness in case of a counter flow heat exchanger also in terms of NTU and capacity ratio. Now in the bottom of this slide we can see that the effectiveness formula for the parallel flow and counter flow, these are given here in terms of NTU and capacity ratio. So in case of the parallel flow, the effectiveness, it is 1 minus e to the power minus NTU multiplied by 1 plus R divided by 1 plus R, and in case of the counter flow, the effectiveness formula in terms of the NTU, it is actually 1 minus e to the power minus NTU 1 minus R divided by 1 minus R e to the power minus NTU 1 minus R. So these two formulas of effectiveness for parallel flow and counter flow in terms of NTU and R, we need to remember to solve the numericals, where the NTU, the number of transfer unit, it is actually UA by C mean, and capital R, it is the capacity ratio, this is C mean by C max. Now two cases can be there when the R equals to 0, that is the capacity ratio, that is C mean by C max, this is equals to 0. So this happens in case of the condensers and evaporators, is boiler. So when the capital R equals to 0, so in that case the effectiveness for the parallel flow and counter flow, this is equals to 1 minus e to the power minus NTU. So such cases are found in condenser and evaporator, in which one fluid remains at constant temperature throughout the exchanger. So in this case C max equals to infinity or undefined, and thus R equals to C mean by C max is equals to 0. So in case of condenser and evaporator, when R equals to 0, in that case the effectiveness formula, it is represented by 1 minus e to the power minus NTU. Now irrespective of the thing that how large the exchanger or how large the overall heat transfer coefficient is, a maximum effectiveness for parallel flow heat exchanger, it is 50%, and for counter flow this limit is 100%. Okay, so these are the things that you need to remember for MCQ question purpose, that the maximum effectiveness of parallel flow heat exchanger, it is 50%, and for counter flow this limit is 100%. And for this reason also, this counter flow is usually more advantageous for a gas turbine heat exchanger. So this next case is when the capital R, that is the capacity ratio, it is 1, which happens in case of typical regenerators. So when R equals to 1, in that case the parallel flow heat exchanger, considering the parallel flow heat exchanger, the effectiveness formula can be written as e to the power minus, effectiveness equals to 1 minus e to the power minus 2 NTU divided by 2. And in case of the counter flow heat exchanger, when capacity ratio this is 1, so in that case, using the L hospital rule, we can write that the it is actually NTU divided by 1 plus NTU. So now this NTU, it is a measure of the heat transfer size of the exchanger. The larger the value of the NTU, the closer the heat exchanger approaches its thermodynamic limit. So this is another physical significance of the NTU. So it is a measure of the heat transfer size of the heat exchanger. And the larger the value of the NTU, the closer the heat exchanger approaches the thermodynamic limit. Now let us discuss some numerical based on this concept of the effectiveness NTU methods. So what the question says, steam condenses at atmospheric pressure on the external surface of the tubes of a steam condenser. The tubes are 12 in number and each is 30 mm in diameter and 10 meter long. The inlet and outlet temperatures of cooling water flowing inside the tubes are 25 degrees centigrade and 60 degrees centigrade respectively. If the flow rate is 1.1 kg per second, so in that case we need to calculate the rate of condensation of steam, the mean overall heat transfer coefficient based on the inner surface area, then the number of transfer units and the effectiveness of the condenser. So these are the four different things that we need to find in this numerical. Now this diagram, it is given here in case of a condenser. So we know that from the concept of the condenser that there the condensing fluid, it remains at constant temperature throughout the heat exchanger, but the temperature of the colder fluid, that can be seen from this diagram also, it is the temperature of the colder fluid, it is gradually increasing from the inlet to the outlet. That is, at the inlet TC1 it is 25 degrees centigrade and at the outlet of the cold fluid it is 60 degrees centigrade. So from the inlet to the outlet, the colder fluid's temperature, it is increasing gradually. So what happens, how this temperature increases for the cold fluid? So this cold fluid, it actually accepts the latent heat part which the hot fluid loses. So gaining that latent heat part from the hot fluid, this temperature of the cold fluid, it actually increases in case of a condenser, and the temperature of the hot fluid, it actually remains at constant temperature, which can be seen from this diagram also. Now here what are the things given, the tubes, 12 number of tubes we are using here. Di equals to 0.03 meter, L equals to 10 meter. TC1 it is given 25 degrees centigrade, TC2 it is given 60 degrees centigrade, TH1 and TH2 is the hot fluid temperature, it is uniform throughout the condenser. So TH1 It is the inlet and outlet temperature of the hot fluid. This will be same, that is 100 degrees centigrade. The mass flow rate of the hot and cold fluid. Mass flow rate of the cold fluid, it is given as 1.1 kg per second. So first thing we need to determine the rate of condensation of steam, that is mH. So here we need to use the concept that is heat lost by the steam, it is heat gained by the water, that is the concept from the condenser that we have discussed just now. So ms, that is the mass flow rate of the steam, and h, fg, this is equals to m dot c, cpc, and the temperature difference for the outlet and inlet of the cold fluid, where hfg, this is the latent heat of steam. At atmospheric pressure 2257 kg per kilojoule per kg. Now substituting these values, in the above equation, we can calculate the rate of condensation of steam. It is ms or m dot s or m dot h. This is we are getting as 257 kg per hour. So using this concept of the condenser, here we have calculated the rate of condensation of the steam, which we are getting as 257 kg per hour. So next we need to calculate the mean overall heat transfer coefficient, that is capital U. The heat transfer rate, it is given by Q equals to m dot c, cpc, and the temperature difference for the outlet and inlet of the cold fluid. Now the mass flow rate of the cold fluid, it is given 1.1 cpc, that is the specific heat for the cold fluid. It is having a default value 4.187 10 cube. And TC2 and TC1, these are given in the question 60 and 25. So using these values, we can calculate the total heat transfer rate. Now again, we know the formula for the total heat transfer rate in terms of the LMTD. This is equals to Q equals to UA theta M. Now this theta M, this is the LMTD. Now this formula for the LMTD, this one we can calculate using this equation, that is theta 1 minus theta 2 divided by ln theta 1 by theta 2. Now all these values of theta 1 and theta 2, which are actually the temperature difference for the inlet and outlet of the hot and cold fluids respectively. So all these values are known to us, so we can put all these values here and we can calculate the LMTD, that is logarithmic mean temperature difference here. And the area, it also we can calculate from 12 number of tubes, that is n multiplied by the pi dl. So this is coming in 11.31 meters square. Now substituting these values in the earlier equation, we can calculate the mean overall heat transfer coefficient capital U, which is coming as 255.9 watt per meter square degree centigrade. So in this way, we using the concept of the LMTD, we have calculated the mean overall heat transfer coefficient. Now the number of transfer units, so that is NTU. So the formula for the NTU, we have seen that it is UA divided by C mean. In a condenser, the C max, it refers to the hot fluid which remains at constant temperature. So that means C mean, it refers to the water. Now in the formula of NTU, we are having the C mean part, so that means the formula of the C mean is equals to mass flow rate and the specific heat of the cold fluid. So the mass flow rate for the cold fluid, it is given in the question, that is 1.8, and the specific heat of the cold fluid, it is having a default value that you need to remember. So putting all these values, you can calculate the heat capacity for the cold fluid, which is coming as 4605.7 watt per degree centigrade. Now if we use the equation of the NTU, that is UA divided by C mean, and as all the values are known to us, or we have calculated in this numerical in the earlier steps, so we can put all these values here, and the final value of the NTU, that is number of transfer units, we are getting as 0.628. And lastly, we need to calculate the effectiveness of the condenser, that is epsilon. So the effectiveness of the condenser, considering the cases that we have discussed earlier. So here epsilon, this is equals to 1 minus e to the power minus NTU. Now the value of the NTU we have calculated just now, 0.628. So the effectiveness of the condenser, it is coming as 0.47. So this is the procedure by which we have calculated all the four number of required things in this numerical. Here we have used the concept of the heat exchanger analysis, the heat loss and heat gain by the hot and cold fluids. But then in case of the this NTU method, here we had to find the overall transfer coefficient, for which we have used the formula and the concept of the LMTD also, that is logarithmic mean temperature difference. Now, after that, while calculating the number of transfer unit, we have used the formula of NTU, that is UA by C mean. For that, based on our concept, we have selected or we have chosen which value, what is the value of the C mean, is it for hot fluid or cold fluid. Then finally we have considered that special case of the effectiveness method, effectiveness formula, and we have used that formula directly to find the effectiveness of the condenser in this numerical. So let us discuss the next numerical. A counterflow heat exchanger is employed to cool 0.55 kg per second, and the Cp is given 2.45 kilojoule per kg degree centigrade of oil from 115 degrees centigrade to 40 degrees centigrade by the use of water. The inlet and outlet temperatures of cooling water are 15 degrees centigrade and 75 degrees centigrade respectively. The overall heat transfer coefficient is expected to be 1450 watt per meter square degree centigrade. Now, using the NTU method, we need to calculate the mass flow rate of water, the effectiveness of the heat exchanger, and the surface area required. So in this case, or in this concept of the counterflow heat exchanger, let us first decide what are the things, let us first write what are the things given in this numerical. The mass flow rate of oil, this is actually the hot fluid here. So the mass flow rate of the hot fluid, it is given 0.55 kg per second. And the specific heat of the hot fluid, this is given is 2.45 kilojoule per kg degree centigrade. Then the TH1, that is the inlet temperature of the hot fluid, this is given 115 degrees centigrade. And the TH2, that is the outlet temperature of the hot fluid, this is given at 40 degrees centigrade. Then the inlet temperature of the cooling water, that is the cold fluid, it is given as 15 degrees centigrade. And the inlet temperature of the hot fluid, it is given as inlet temperature of the cold, outlet temperature of the cold fluid, it is given as 75 degrees centigrade. And the overall heat transfer coefficient value, it is also given as 1450 watt per meter square degree centigrade. So these are the things actually given here. So first, when using the NTU method, we need to calculate the mass flow rate of water. So that means the mass flow rate of the cold fluid. Now the mass flow rate of water can be calculated using the overall energy balance for the hot and cold fluids respectively. So that energy balance equation is actually m dot Cph Th1 minus Th2, this is equal to m dot C Cpc Tc2 minus Tc1. This is the formula of the mass flow rate of water. as the our energy balance equation. So here all the values are known to us except the mass flow rate of the water. So putting all the other values in this equation, in this energy balance equation, we have calculated the mass flow rate of the cold fluid. This is coming as 0.4 kg per second. So let us discuss the second part of this numerical. So it is the effectiveness of the heat exchanger. So how to calculate the effectiveness of the heat exchanger, that is the epsilon for this counter flow heat concept, counter flow heat transfer. Now the thermal capacity of the cold stream, that is the cold fluid, and it is a cooling water here, which is Cc, that is the heat capacity. The formula is m dot c, that is the mass flow rate, multiplied by the specific heat of the cold fluid. So the mass flow rate is given in this numerical. So that is actually we have calculated in the first part of this numerical, that is 0.4, the mass flow rate of the cold fluid, and specific heat of this cooling water, that is known to us, that is 4.18. So the thermal capacity of the cold water, this is coming as 1.672 kilowatt. Now the thermal capacity of the hot fluid, that is the oil, so it can be calculated in the similar manner using the heat capacity rate, that is m dot h multiplied by cph. So the m dot h, that is the mass flow rate of the hot water, and the not hot water, that is the hot oil, that is given here as the 0.55 kg per second, the mass flow rate, and the specific heat of the hot fluid, that is we can see in the first line of this numerical question, it is given specific heat of the hot fluid, that is the oil, it is 2.45. Now using these values we can calculate the thermal capacity of the hot fluid, that is the oil. This is coming as 1.347 kilowatt. Now here we can see the thermal capacity of the cold fluid, it is greater than the thermal capacity of the hot fluid. So now the effectiveness formula of this counterflow heat exchanger, this is actually from the concept we can write that actual heat transfer divided by maximum possible heat transfer. So Q by Q max, so this is actually TH1 minus TH2 divided by TH1 minus TC1. So using these values which are given in this numerical, we can calculate the effectiveness of the heat exchanger for this counterflow type. It is coming as 0.75. And the last part of this numerical, here we need to calculate the surface area required for this counterflow heat exchanger. Now here C mean, that is the minimum heat capacity, which we have seen in the earlier part. There we have calculated the C mean, that is actually the CH, that means the heat capacity of the hot fluid, it is coming as 1.347 kilowatt. So if CH is the C mean, so in that case CC, that is the heat capacity of the cold fluid, it is actually the C max here. So which we have calculated in this earlier part of this numerical, which is 1.672 kilowatt. Now if C mean and C max, these are known to us, then we can calculate the value of the R, which is actually the capacity ratio. So the formula of the R, it is C mean divided by C max. Now the value of the C mean, it is 1.347 kilowatt, and value of the C max, it is 1.672 kilowatt. Now putting this value in the formula of the capacity ratio, we are getting that the value of R, or the capacity ratio, it is 0.806. Now for this counter flow heat exchanger, This is the formula that we have seen earlier. So this formula we need to remember and we need to use here in this numerical, because it is based on this counterflow heat exchanger concept. So the formula of the effectiveness for this counterflow heat exchanger, this is equals to 1 minus e to the power minus NTU into 1 minus r divided by 1 minus r e to the power minus NTU 1 minus r. So this is the new final equation of the effectiveness for the counterflow heat exchanger in terms of NTU and capacity ratio, where NTU equals to UA by C min and capacity ratio it is C min by C max. Now from this equation, if we do some rearrangement, then first to find the value of the NTU, we can put all the other values as the effectiveness, then the capacity ratio. All these values are known to us. So you can find the value of this NTU, that is the number of transfer unit here, from this equation of the counterflow heat exchanger, which is coming as 2.365. So this is the value of this number of transfer unit here for this counterflow heat exchanger. Now as the formula of the NTU, that is number of transfer unit, it is known to us, that is UA divided by C min. Now using this formula, we can calculate the surface area required for this counterflow heat exchanger. So the formula of NTU, it is UA divided by C min. Now the value of this NTU, that is number of transfer units, it is we have calculated just now, which is 2.365. Next, the value of the overall heat transfer coefficient. So this value of the overall heat transfer coefficient, it is actually given in this numerical. See, in this numerical question, the value of the overall heat transfer coefficient, it is written as 1450 watt per meter square degree centigrade. So this value of overall heat transfer coefficient you can write here. Then the value of the surface area we need to calculate. Then the value of the C mean, that is actually we have calculated earlier in the second part of this numerical, and the value of C mean, it was the thermal capacity of the hot fluid actually, because the thermal capacity of the hot fluid, it is lesser compared to the thermal capacity of the cold fluid. So this thermal capacity of the hot fluid being the C mean, we have seen the value is 1.347 kilowatt. So you can write that in watt only. So the value of the surface area required for this counterflow heat exchanger, we can calculate from this equation of the NTU, and finally this value of the surface area, it is coming as 2.197 meters square. So this is the way here to find the mass flow rate of this cold fluid, then the effectiveness of the heat exchanger using the NTU concept, and the surface area of the required. Here also we have used the effectiveness and NTU formula for this counterflow heat exchanger. So today in this lecture we have seen the concept of the effectiveness and NTU method. So this effectiveness is actually the ratio of the actual heat transfer divided by maximum possible heat transfer, and the NTU also we have seen the number of transfer unit. It represents the size of the heat exchanger. Next, for the parallel flow and counter flow heat exchanger, we have derived the equation of the effectiveness in terms of NTU, and R, that is the capacity ratio. So the NTU formula, it is UA divided by C mean, that is the minimum heat capacity or thermal capacity in between the hot and cold fluids, and R, it is the ratio of the C mean divided by C max. So it is known as the capacity ratio. Hence, based on this formula of the effectiveness and NTU, we have discussed some numericals. So these are the things that we have discussed today in this lecture. So this is the end for this lecture.